This is the second half of the accumulation function. A lot of this one I'm going to have you guys do on your own, and then I'll just kind of put the answers up so you guys can check them. But I want you guys, it's very similar to the one we did in yesterday's video, so I want you guys to kind of practice doing it on your own. So as a reminder of what we did yesterday, it says let f of x, capital F of x, equal the integral from 0 to x of f of t dt. Remember, that's called the accumulation function. And it says f of x, little f of x, is this function graphed right here, consisting of lines in a semicircle. So remember, this is a graph of the first derivative, lowercase f of x. When I take its integral, it's putting me back up to the original function. So the relationship between these two functions is that the function inside of the integral is the derivative. When you take its integral, it puts you back to the original function. That's a very, very, very important concept for you guys to remember, because a lot of times if you can make that connection, some of the questions on the AP test become super, super easy because of it. So please make sure you make that connection, that f of t dt is the derivative and f of x, once you take this integral, is the original function. So it says find the following. I'll do a couple with you guys, and then I'll have you guys do the other ones on your own. So let's do the first, let's do b together. It says f of 2. So the integral, if I plug in 2 up here, this would be the integral from 0 to 2 of f of t dt. So the integral from 0 to 2 would be from here to here, if I look at that piece of it. I have this quarter circle that has a radius of 2, so the area of a circle is pi r squared. The radius is 2, therefore it's pi times 2 squared, or pi times 4. So 4 pi, but since this is only a quarter of the circle, it would be 4 pi over 4, which is just pi. Therefore, the f of 2 is equal to pi. F of 4 would be plugging in 4 up here, the integral from 0 to 4 of f of t dt. Well, we know the integral from 0 to 2 is pi. This is another quarter circle, so this one also has an area of pi. So if I'm accumulating the area, I get that pi plus pi is equal to 2 pi. All right, I'll let you do some more of those on your own. I'm going to come down here and look at f prime of 4, I should say. So remember that the derivative, if I'm taking the derivative of f prime, it's like taking the derivative of the integral. Remember that the derivative and the integral are inverse operations. They're inverse operations, and so the derivative and the integral would essentially undo each other. So the derivative of this function is just equal to f of t dt, the first derivative. So they're essentially saying, what is the derivative equal to at 4? Or in other words, what is this function equal to at 4? So I look here and I go here 0, 1, 2, 3, 4. This function at 4 is equal to 0 because it literally goes through the point 4, 0. So f prime of 4 is equal to 0. Let's try one more. F prime of 2. This function is the derivative of capital F of x. Therefore, to look at f prime of 2, I would come over here to 1, 2, and then look for where the function is. It's up here at 1, 2. So f prime of 2 is equal to 2. All right, please pause the video so that you guys can try and fill in the rest of these ones that we haven't gotten together. I'll put the answers up here, and you guys can check your work. All right, so here's the rest of the answers so you guys can check them and make sure that you're doing them correctly. The first one, f of 0 is equal to 0. Remember, the integral from 0 to 0 would be 0 because we're not going anywhere. We did this one. F of 6 would be adding together all of this. So pi plus pi was 2 pi, and then minus 2. Can't combine those. 2 pi minus 2 is the final answer. Oh, I forgot one. F of negative 1 is equal to 1. Oh, my bad. I need to change some of these answers. I made a mistake, and let's talk about why. If I write this out, and this is something you have to be careful about, if I want f of negative 1, this would be the integral from 0 to negative 1 of f of t dt. Now, what I was not paying attention to is the fact that we are reading these backwards. 0 to negative 1 is an upside-down integral from a larger number to a smaller number. So if I want to fix that, that would be the negative integral from negative 1 to 0 of f of t dt. So, even though the area is 1, because it's a negative, since I was reading it backwards, I have to go negative. So this should be a negative 1. Excuse me. F of negative 2. Again, same thing. F of negative 2, we've accumulated 1 unit and then 2 more units. That's 3 units of area, but because we're reading it backwards, that's a negative 3. For f of -3, we're going backwards. Here's 1 unit, 2 units, and then notice that here we have a positive 1/2 and a negative 1/2. If I add together positive and negative 1/2, those are going to add back to 0 again. So this would be 1 unit, 2 units, and then these that go away is a total of 3. And again, we're reading it backwards, so it's -3, because we're going from 0 to -3, which is a larger number to a smaller number. For h, f of -4, we're reading it backwards. So we have 1 unit, 2 units, these ones cancel each other out, and then another -1. So that's 1 plus 2 is 3, 0, so that's still 3, and then -1 would be 2, and since we're reading it backwards, it's -2. Then we got into the derivatives. So we already did this one. F prime of 4 was equal to 0. F prime of 2 was equal to 2. This one says F prime of 6 is equal to -2. Here's 6 over here, and it's equal to -2. And then F prime of -3 is right here. F prime of -3 was equal to -2. Notice that the derivatives don't affect which way you're reading it, only the original function. So if I plug in a number that's smaller than 0, I have to take that into account by putting a negative in front of it. Don't forget about that. All right, M says, on what subintervals of the interval from -4 to 6 is f increasing and decreasing, and justify your answer. I'm just going to write the intervals so you guys can check your work in that regard, but justifying your answer we'll talk about, and I expect you to write it into your notes, but I'm not going to write it into mine. So increasing. Oops. This function is increasing wherever the derivative is positive. And remember, this is the derivative. This is f of t dt, or f of x. And so the derivative is this function. So wherever it's positive, the original function, capital F, will be increasing. So that's from -2.5 to, let's see, it goes down to 0 at 0, but it's still positive after that. So we're going to say it goes all the way to 4. And then it's decreasing wherever the derivative is negative. So that would be from -4 to -2.5. And then again, from 4 to 6. And again, I won't write out the reasoning for that, but I want you guys to put it into your notes that we're looking for wherever the derivative is positive, the original function is increasing. Wherever the derivative is negative, the original function is decreasing. For part N, it says, where in the interval does f achieve its minimum value, and what is the minimum value? So remember that a function will have a minimum value wherever its derivative has a 0 that changes from negative values to positive values. So that occurs right here. And if you remember the first part of this problem for today, we wrote down that the value here, well, actually we didn't write down this value right here, but we said that this had an area of -1, and that when we added this, it was up to -3. And then if we had added on this one, which it didn't ask us for, but if we had added on this one, it would have gone down to -3.5. So yes, this is a minimum value. After that point, it started adding back up again, because since we were reading it backwards and it was negative areas, those turned into positive areas, and it went back up again. So a minimum value occurred at x equals -2.5. And the minimum value was, and again, it didn't ask us for it, but we could figure it out right now. Since we're reading it backwards, like we said, this is an area of 1, this was an area of 2, this was an area of 1/2. So if I add them all together, I get 3.5. And since we're reading it backwards from 0 to -2.5, it's a -3.5. And then where in the interval does it achieve its maximum value? A maximum is wherever the function equals 0 and changes from positive to negative. So that occurs here. Don't forget that it could also occur at endpoints. You also have to test endpoints. But if you looked at the values, remember it was 0 here, and then it accumulated a pretty large positive area. This one didn't go down as much as this one went up because the area here is much larger. So this wasn't a minimum because of that. And then going backwards, remember we were accumulating this negative area, and this positive area put us back up again, but only closer to 0, not too high. So from 0, coming this way, we have a 0 here that changes from positive to negative values. Therefore, this area that has accumulated puts us at our maximum right here, which is at x equals 4. And the maximum value is f of 4, and we said that was equal to 2 pi. Next question. Where in the interval is f concave up and concave down? Again, I'll just write the concavity intervals. So it's concave up wherever the derivative is increasing, which is from -3 to -2, union 0 to 2. It's concave down wherever the derivative is decreasing, which is from -4 to -3, and from -1 to 0, and again from 2 to 6. And there's only one place where it's neither concave up nor concave down, and that is from -2 to -1, because it's a constant function there. And then it says, where does f have points of inflection? Points of inflection wherever it has maxima or minima. So x equals -3. Again, it's not really a point of inflection at -2 to -1, since it's an interval where it's changing concavity. It has a point of inflection at 0 since there's a minimum, at x equals 2 since there's a maximum, and I think that's it. And then last but not least, they want us to sketch a function. So if we can put some of these points on. At 0, it's 0. We said at 2, it was equal to pi. And notice, by the way, there's this little thing right here that says each tick mark on the y-axis is 2 units. So let's count by 2. If this is pi, that would be 3.14. So at 2, it's about 3.14. So if we count up, there's 2 and then 4. So it's right about in the middle of those two, right about there. At 4, it was equal to 2 pi, which is 6.28. So 2, 4, 6.28 puts us about right here. Then we said 2 pi minus 2, because this had an area of 2 units, so putting us back down 2 units. So by the time we got to 8, we were back down to 4.28. 2, 4, 4.28, sorry about there. Then going in the negative direction, we had accumulated -1 unit of area. Then by the time we got to here, we had accumulated -3 units. So at -3, it was -3 units. Oops, we're counting by 2s, huh? My bad. At -3, it was -3 units. At -3.5, it was -3.5 units. Oh, no, sorry, that was -2.5. Just kidding. Let me fix that. Right there. At -3, we were back up to 3 units again. And then by the time we got to -4, we were back up to 3 plus 1, -2. Sorry, that wasn't perfect, but you get the point. It was concave down at first, then it changed to concave up, and then it was a constant from -2 to -1, straight line. Then it was concave down again from -1 to 0, concave up from 0 to 2, concave down the rest of the way. So again, you can see how this function appears, where we have an absolute minimum over here at, excuse me, an absolute minimum over here at 2.5 comma -3.5. We have an absolute maximum right here at 4 comma 2 pi. And then we didn't really have too many other minima and maxima in there. Actually, I don't think we had any, but we did have some points of inflection. All right. And I believe that's it for today. Yep. All right, that's it.